Okay, we'll get started. So, today's the last. So what we have next week. So the chapter 7 homework is due next week on Monday. Next week on Monday, we will have a review of chapters 5, 6, and 7, and the quiz on chapter 7. The lab period on Monday is for makeups. On Wednesday, we have the exam for chapters 5, 6, or 7. 5, 6, 7. That exam will be on Wednesday next week. The quiz on chapter 7 will be on Monday next week. The lab on the 27th is for makeups. All the grades on all the labs and the quizzes for chapters up through 6 are posted on Blackboard. Sorry, there was a delay on the chapter 6 quiz grades. I forgot. I entered them all, and then you need to press another button to make them visible. It's really annoying. They changed the system and I hate it. If you need to make anything up, if it has a 0, I'm available also on Mondays, Tuesdays, and Wednesdays from 10:30 to 1 and Thursdays from 11:30 to 1. Any questions about that? If you need to take, yeah. So we were talking about various elements and what makes an element stable and things like that. Now, on Earth, naturally occurring, you only get elements up to basically uranium, 92. This is not 100% correct. There is a small amount that was recently discovered that there is a small amount of natural plutonium, but it's actually naturally synthesized, which is kind of weird. So all of these elements, all transuranic elements, are synthesized. If you encounter them, they've been synthesized. They're created by bombarding a lighter nucleus with alpha particles or neutrons. For example, you could bombard uranium-238 with a neutron and get neptunium-239 and an anti-electron. Or you can bombard bismuth-209 with iron-58 and get, I have no idea his name. Adrian. MT 266 and a neutron. So that's how you can get heavier elements. And we've gotten up to 108, I believe. Maybe no, 118, sorry. I think successfully nuclei have been synthesized up to 118. I can't remember if they've gone beyond that. But most of the very large numbers are like, they last a fraction of a second. They're incredibly unstable. So, how did all the nuclei we encounter come into being? Well, if we're talking about hydrogen, helium, or lithium, hydrogen, helium, and lithium are thought to have been formed in the Big Bang. Most of the lithium you encounter was actually formed through other processes because the Big Bang formed a very, very small amount of lithium. But most of the hydrogen and helium in the universe was formed during the Big Bang. There was a period during the Big Bang where the universe was hot enough and dense enough for fusion to occur, and hydrogen fused into helium. And that's sort of the raw material of the universe. Interestingly enough, almost all the helium on Earth was not formed in the Big Bang. It actually comes from radioactive decay of elements on Earth. Because if you release helium into the atmosphere, it goes away. From beryllium up to iron are mostly made in the cores of stars via fusion. And atoms heavier than iron are formed during supernova explosions, whether there was an abundance of neutrons and medium-sized atoms. In fact, the whole process has some extra steps for certain elements. It's complicated. It's more complicated than we can cover here, but in general, supernovas are required. For some elements, you also need like merging neutron stars as an additional step to form them, to generate the kind of bombardment necessary to generate them. So radionucleotides are used for a whole bunch of purposes. They have many uses in medicine, chemistry, biology, geology, agriculture, and industry. So, for example, one medical use is use of the radioactive isotope of iodine, iodine-123. It's used for a diagnostic measurement of the thyroid gland. So if you want to study how your thyroid gland uses iodine to do its stuff. So if you want to study how the thyroid gland is taking up iodine, you have someone eat some iodine that has some radioactive iodine in it, and then you can study how that iodine is moving through the person's body because it emits radiation, which you can detect. You may have heard after like nuclear disasters, people eating iodine pills. That is to protect your thyroid gland. Because one of the things that can be released when you have nuclear fallout is radioactive iodine. So if you take iodine pills of not radioactive iodine, your thyroid gets full of iodine, and it doesn't take in the radioactive stuff, which could give you thyroid problems. There's also a treatment of the thyroid where you consume a lot of radioactive iodine to kill your thyroid gland if something is very wrong with it. Instead of having it surgically removed, you basically use the fact that it absorbs iodine to concentrate the radiation in the thyroid gland and kill it. And then Americanium-241 is a synthetic transuranium radionucleotide that's used in smoke detectors. Less these days, but one of the common ways you did a smoke detector is you had some of this Americanium-241. It emits radioactivity. If there's smoke, the smoke blocks what it's emitting. That changes the what's detected. So what you have is you have a radioactive source and a detector. It's emitting radiation. If smoke comes in, it blocks the radiation. That sets the alarm off. The smoke detector, ions are traveling across this gap from the radioactive source. They allow current to flow. If smoke comes in, it blocks them. The current gets reduced. That causes an alarm. And in both chemistry and biology, we often use radioactive tracers. Carbon-13 and hydrogen-3 used to tag an atom within a molecule. So you can study things like the reaction pathways of drugs and hormones. In geology, the predictable decay rate of radioactive elements in rocks and minerals allows us to date rocks and minerals. And in industry, tracer radionuclides help manufacturers test durability. They're also used as sources of radiation for either radiation treatments or things like X-rays and imaging purposes. Now, we've been talking about relatively simple, a little bit less dramatic forms of the nuclear reactions. But the most dramatic nuclear reactions are fission and fusion. Nuclear fission is where you have a big nucleus that can be rendered unstable by, say, whacking it with a neutron, and it splits in two. And maybe throws off some additional material, with a couple neutrons and some energy. So fission is the process by which a large nucleus splits into two intermediate-sized nuclei with the emission of neutrons and the conversion of mass into energy. So you get out more energy than you put in for fission. So for example, if you stick a neutron into uranium-235, it becomes uranium-236, which is unstable and will split into two smaller nuclei, emitting several neutrons and releasing energy. So these are two of the possible outcomes. Uranium-236 can split into xenon-140 and strontium-94, or tin-132 and molybdenum-101. The first one throws off 2 neutrons, the second one throws off 3 neutrons. But these neutrons are emitted and can hit other uranium-235s and turn them into uranium-236, which will then split and emit more neutrons. And that can cause a chain reaction. So here's another example: uranium-236 and krypton-88 plus barium-144. What do you left? Well, 88 plus 144. Well, the 36 plus 56 gives you 92. And so the atomic numbers are balanced. 88 plus 144 is 232. So there are 4 atomic mass units left. So 4 additional units of mass are needed on the right, and that's going to be 4 neutrons. So 4 neutrons. The missing particle has to have an atomic number of 0 and a mass number of 4. No single particle exists with these properties, but that missing particle is actually 4 neutrons. So this is spitting out a whole bunch of neutrons. So there's sort of a couple of ways you could use this. A couple of ways this is used out in the universe, out in the world. You can emit here's another one. Uranium-236 goes to strontium-90 plus xenon-144 and 2 neutrons. Okay. The atomic numbers are not balanced. So the atomic number for the unknown must be 54. The masses are not balanced. The mass of the unknown must be 144. That's xenon-144. So the products of fission are always radioactive. They're always unstable. Some products have half-lives of thousands of years, which can lead to the issue of nuclear waste disposal, which is tricky, but not as bad as people make it seem. Because we can safely and securely store nuclear waste, and really you can just put it in a very deep hole. The biggest problem is political. It's not engineering. And relatively large amounts of energy are produced and neutrons are released. So you can do this process. So what you can do is you can set up a chain reaction. One initial reaction triggers a growing number of subsequent reactions. So so if you hit a uranium-235 with a neutron, it turns to uranium-236, splits, generating a couple of neutrons. Those can hit a couple more uranium-235s, and so on. So in the case of uranium-236, each fission emits 2 neutrons. Each of these 2 neutrons can hit another uranium-235, resulting in the fission of 2 additional uranium-235 nuclei and the release of energy at 4 neutrons. And more fission can occur, and the chain can get bigger and bigger. And if you set this up so that every reaction starts 2 more, that's how you make a nuclear bomb. So here, uranium-235 absorbs a neutron and initially changes into uranium-236, then immediately undergoes fission, releasing 2 neutrons and energy. So if you set this up so that every neutron, so that every time one fission occurs, it starts more than one fission, ideally 2, but more than 1. Then this is going to go faster and faster and faster, be uncontrolled, and you get an explosion, a violent, dangerous explosion. So if all the emitted neutrons hit another uranium-235 nucleus, this results in an increasing number of emitted neutrons, fusion reactions, and energy relays. So you have an expanding chain reaction. Then that gets bigger and bigger and bigger. And this is how you blow up a city. But if you set this up so there's not so much uranium-235 around, you've got material around to control the rate that things get absorbed. So every fusion just starts another fusion. Well, then you've got a nice steady state, which you can use to generate heat and boil water and generate electrical power. And that's what a nuclear power plant does. So a steady release of energy can be attained where each fission event causes only one more fission event. This is sort of a self-sustaining chain reaction or a controlled chain reaction. This would be an uncontrolled expanding chain reaction. This would be a controlled chain reaction. And for a self-sustaining chain reaction to proceed, the correct amount and concentration of fissionable material needs to be present. You use much less concentrated uranium-235. You have more uranium-238 around. And if there's too much fissionable material present, an expanding chain reaction occurs. If there's too little present, the chain reaction will stop. And you can add or remove other things into the mix, basically, to affect the rate at which it proceeds. So you can make it more likely for neutrons to hit things and activate them, or less likely. That's what, you can add things that absorb neutrons to slow down and stop your chain reaction. That's what control rods are. You can also add things in that will help speed up and make your chain reaction work better. These are called moderators. So the critical mass is the minimum amount of fissionable material necessary to sustain a chain reaction. For uranium-235, that's about 4 kilograms of pure uranium-235. So if you had a 4 kilogram ball of uranium-235, it would undergo a chain reaction. A subcritical mass is one where no chain reaction occurs. A supercritical mass is one where an expanding chain reaction occurs. And the way you make a nuclear bomb, well, the simplest way is you take 2 subcritical pieces, and when you want them to go boom, you slam them together to form a supercritical lump. The other way you can do this is that you can take a subcritical ball and implode it so that its density increases, and that changes what the critical mass is, and it becomes supercritical. And those are like the 2 ways you can make a nuclear weapon. Both of those have been developed. So uranium. Natural uranium contains 99.3% of uranium-238 and only 0.7% of the fissionable uranium-235. Therefore, in order to use uranium as fuel for or for making weapons, you need to enrich it. You need to get more uranium-235 and less uranium-238. So in order to create either a self-sustaining or expanding chain reaction, you need to increase the concentration of uranium-235 and remove some of the uranium-238. You need some way to separate them. There are several ways to do this. The original way that it was done during World War II involved actually particle accelerators. But in US nuclear reactors, the uranium-235 has been enriched to about 3%, which is enough for a self-sustaining chain reaction. While in contrast, nuclear weapons require an enrichment of around 90% for that sudden release of energy. So the stuff that's used as nuclear fuel is nowhere near enriched enough to be used as a weapon for an actual nuclear explosion. I mean, you make dirty bombs out of it, but that's something completely different. So in order to create a fission bomb or an atomic bomb, you need a supercritical mass of fissionable material. It needs to be formed and held together. So the general idea is that subcritical portions of the fissionable material are held apart until detonation. And then a conventional explosion is used to bring these subcritical segments together to create a supercritical mass capable of an explosive release of energy. And this sudden release of energy is due to an expanding chain reaction of the fissionable material, making the big boom. Nuclear reactors, on the other hand, want to have a controlled and continual release of fission energy. So within the reactor core, you have long fuel rods and control rods. The fuel rods contain the fissionable material. This is when fission occurs, this gets hot, and then it boils water, which spins a turbine, because that's like how the vast majority of power plants work. We boil water to create steam to spin turbines. The control rods, on the other hand, will contain some sort of neutron-absorbing material, such as boron or cadmium. These control the rate of nuclear fission and therefore the amount of heat produced. So when you insert the control rods, the neutrons don't make it to other fuel rods. They get absorbed by the control rods, and that slows down the rate of fusion, stabilizes the reactor. There are also things called moderators, which slow the neutrons down so they're more likely to interact with another uranium-235. And these speed up the rate of reaction. So by controlling how much moderators you have and how much control rod you have, you can control your rate of reaction. So you have some sort of fuel rod assembly, and then you have control rods that slide in and out of the fuel rod assembly. And inside the fuel rod, you have pellets that are usually made of uranium oxide, because uranium oxide is easier to work with than metallic uranium, because it's just like a powder. So you can pack it into little pellets. And that is your nuclear reactor. Pressurized water flows in, gets very hot, flows out, goes through a heat exchanger to heat other not so pressurized water, which boils, generates steam, spins a turbine. So that the water that's in contact with the nuclear fuel never leaves that closed loop system. They have one loop that heats another loop just to ensure that no contamination spreads. And since the fission rate in the fuel rods can't be directly controlled, you insert or remove the control rods between the fuel rods to control the number of neutrons being absorbed. And the reactor core is basically a heat source. This is one style of reactor. There are a few other types. There's a new one called the pebble bed, which has the nice property that it can't melt down. But the reactor core is basically a heat source. The heat is continually removed by the coolant, water flowing through the core. The heat is used to generate steam in the steam generator. Steam turns a generator that produces electricity. So you have a nuclear reactor, a closed loop of hot water that heats another loop of water that spins a steam turbine, which then condenses after it goes over cooling coils from cooling water You can see these, the outside cooling water is like double isolated from the hot water circuit. So the hot water circuit is completely contained, allowing no radioactive contamination. The modern nuclear reactors are incredibly safe. And the reactor's coolant, water, serves two critical functions. It transfers the heat from the reactor core to the steam generator, because you don't want your reactor core to get too hot and melt. That is what a meltdown is. It is literally when the core of your reactor melts. It is bad. And it serves as a moderator. So the neutrons that are initially emitted from the fuel rods are moving too fast to efficiently cause uranium-235 fusion. So if you slow them down a bit, they work better. After they collide with a few hydrogen molecules, the neutrons have slowed enough to induce uranium-235 fission more efficiently. And so they function better. Now, there are potential dangers with a nuclear reactor. The amount of heat generated needs to be controlled. The fission rate is controlled through the insertion or slowing down or withdrawal, speeding up of the control rod between the fuel rods. And if you fail to control your heat, you're going to have a steam explosion, which is bad, and you get Fukushima. Basically, all their coolant systems got broken by the tsunami because they hadn't had stuff upgraded. It was an old power plant. And then the heat must be continually removed from the core. The heat is removed by the circulation of the coolant. Basically, the circulation stopped at Fukushima because the pump stopped working and their backup power got flooded as well. An improper control or removal of core generated heat can result in the fusing or meltdown of the fuel rods. And then you get an uncontrolled fissioning mass that will cause a steam explosion, which will distribute all the fission materials, and it will melt through the bottom of your reactor and do all kinds of horrible things. And this happens when you turn off all your safety systems. And then when you have a not very well designed reactor, turn off all your safety systems and then panic when the alarms go off. And then you get Chernobyl. Like, Chernobyl happened because huge numbers of safety systems were turned off. But yes, and it will melt through the floor of the containment structure. And at this point, the extremely hot and uncontrollable radioactive material will enter the outside environment, things like the ground, water, atmosphere. It's incredibly hot and getting hotter. So it will boil groundwater, spreading stuff around. It's just not good. So 3 nuclear accidents with commercial power plants have occurred. There are other nuclear accidents, but they're all generally with research things. They're all very small. But 3 with commercial power plants have occurred. 3 Mile Island in Pennsylvania in 1979. Chernobyl in Ukraine in 1986, and Fukushima Daiichi Generating Facility in Japan in 2011. At 3 Mile Island, an accidental shutdown of the coolant led to a partial meltdown. Basically, nothing bad happened. Nothing dangerous was released. The plant was damaged. But some tiny amount of barely radioactive gases were released. It wasn't a big deal. At Chernobyl, a complete meltdown occurred due to all kinds of terrible decisions. Poor human judgment and design problems. So the part of the problem was that this reactor was designed in a way, wasn't the best design, but also a whole bunch of the safety systems and stuff had been turned off earlier at Chernobyl. Like there's a whole timeline you can go through to see how many horrible mistakes have been made. So 3 Mile Island was as bad as it was, partially because it had the most confusing interface and they couldn't tell exactly what was going on. Because good and bad, some lights when it was on was good, some lights when it was on was bad. They had tons of alarms going off all at once. It was very confusing. And then at Fukushima, the plant was somewhat out of date and had not gotten updated, and there was a severe earthquake which caused power loss, and then tsunami waves disabled all the backup generators. And this resulted in a partial explosion of 3 nuclear cores, causing a hydrogen gas buildup, which exploded, which released radioactive material. I don't think anyone died from Fukushima because the response was quick and stable. Chernobyl was just bad. But, like, just as an example, nuclear power is surprisingly safe. Coal power plants release more nuclear material than nuclear power plants do. They release more radioactive material into the environment than nuclear power plants do. Because there's radioactive material in coal, and it goes up the smokestack. Like, really, nuclear power is not that bad. And every one of these incidents has helped us design better, safer plants. So, there's something called a breeder reactor as well. A breeder reactor is a reactor that's not designed primarily to produce power. It's designed to produce other transuranic elements. So besides uranium-235, another fissionable nuclide is plutonium-239. You can make plutonium-239 by bombarding uranium-238 with fast neutrons. So plutonium-239 is generated in nuclear reactors. Because there's uranium-238 around, the neutrons slam into it, turn it into plutonium. In a breeder reactor, you've optimized your reactor to have lots of fast neutrons hitting uranium-238, generating lots of plutonium. Then you can separate out the plutonium-239 and use it in an ordinary nuclear reactor or in weapons. So this is how we make plutonium. So plutonium-239 is a natural byproduct of a nuclear reactor. 20 breeder reactors running for a full year produce enough plutonium-239 to run another reactor for a full year. They run at a higher temperature than conventional reactors and use liquid sodium as a coolant. There's also some designs for reactors that use thorium. There's some discussion about using thorium reactors and things like that. And the advantage of thorium reactors is that thorium is really common. And the whole cycle would be safer. It uses some uranium to cause the thorium to turn into a fissionable form, and then you can use that. Yeah. The next generation of nuclear reactors is a pebble bed gas reactor. This is a little out of date. China made one just this year. I think it was this year. It might have been last year. But within the last year, they started up the first pebble bed gas reactor. They use graphite uranium pebbles instead of fuel rods. And the reactor is cooled by non-explosive helium gas instead of water. Helium is inert and doesn't become radioactive. And graphite is a good moderator, slowing down the fission neutrons. And basically the way it works is that pebble bed gas reactors fail safely. Something goes wrong, they stop working. They fail into a basically into a subcritical state. So these are designed to be much, much safer. Basically the way that they fail, they will cool themselves and you don't get a meltdown. Basically, you can just dissipate heat on their own and you can shut them down by just removing the pellets. Now, the primary way that we get energy out of the Earth is actually from the sun. The sun generates its energy via fusion. So we talked about fission, which is where big nuclei split apart. Fusion is the opposite. This is where smaller nuclei combine to form bigger nuclei. This is the process that formed maybe not most, a lot of what makes you up. Everything except the hydrogen. There's a bunch of hydrogen. But all the carbon and oxygen and things like that all form via fusion. So fusion is a process by where smaller nuclei combine to form larger nuclei, and this releases energy. It does not require a critical mass. It will fundamentally fail safely because if it melts, it just like, it doesn't create significant quantities of radioactive material in any way. And when it fails, the gases leak out and the fusion stops. And if the gases leak out, it's not a big deal because they're just hydrogen. The fusion is the source of energy for the sun and other stars. In the sun uses this wonderful process called the proton-proton chain, where it takes 4 hydrogen nuclei, combines them into a helium nuclei, 2 positrons, 2 neutrinos, and some energy. This process starts with as multiple steps and is just not in any way practical to do on Earth. Basically, the proton-proton chain works in the sun because the center of the sun is very, very hot and, most importantly, very, very dense. So it can use very inefficient methods because it gets lots of tries. Because it's so dense, you know, if a collision only works 1 in a million times, but you have a billion collisions, you know, a second, you're good. That's what the sun is doing. It makes very, very dense, very, very hot. On Earth, we can't get the densities they have at the center of the sun. So we have to make it even hotter. And so it turns out making nuclear fusion on Earth that puts out more energy than you put in is really hard. So here are some examples of fusion reactions. This is a deuterium-deuterium reaction, which is the primary reaction that is planned to be used in power plants on Earth, where 2 deuterions, deuterions, so hydrogen 2, merge to form a triton and a proton. Also, a deuterium and tritium can fuse to form helium and nitrogen, which is sort of a next step that can occur. I mean, helium and a neutron, sorry. Why are they saying helium and a neutron? That's a deuterium-tritium reaction. So those are the sort of reactions that you'd have in a nuclear reactor, a nuclear fusion reactor. The products of these are all relatively safe. I mean, tritium's radioactive, but it's not super dangerous or anything. We put it in gun sights. I mean, so this is deuterium-tritium fusion reaction. This is the primary one that's also used in thermonuclear weapons because this pumps out a lot of energy, if you can pull it off. The problem with nuclear fusion, so okay, we can do nuclear fusion that puts out more energy than we put in, but only in an uncontrolled manner. That's what an H-bomb is. The problem is that the repulsive force between 2 positively charged nuclei is very great. And to overcome these strong repulsive forces and initiate fusion, the particles need to be heated to extreme temperatures. In stars, it's like 10 million Kelvin. It can be quite a bit higher temperatures on Earth because the densities are much lower. And at these extreme temperatures, hydrogen atoms will only exist as a plasma. The electrons have basically been stripped off. You have a gas of charged particles. And that plasma then has to be controlled magnetically, because you can't let it touch anything because it is millions of degrees in temperature. You can't build a tank to hold million-degree fluid. The plasma needs to be confined at a high enough density for protons to frequently collide. And even with today's technology, it's a significant challenge to reach the necessary temperature and confinement requirements. So it's quite possible to achieve fusion. Like, there was a 12-year-old who did it. There's been more than one 12-year-old who did it. But that kind of fusion is not generating power. You have to put in more power than you get out. It turns out the real tricky part is not spending so much energy on containment and heating and then extracting. There's two steps. One, actually getting more power out than you put in, which can be tricky. And two, extracting the power you get out. Because you have to have some way to get that energy out of the plasma that you can't touch, which could also be difficult. Another way that they do nuclear fusion is something called inertial confinement, where simultaneous high-energy laser pulses from all sides cause a fuel pellet of deuterium and tritium to implode, resulting in compression and high temperatures. And if the pellet can be made to stay intact for sufficient times, nuke fusion is initiated, and research into this method is conducted at Los Alamos and Lawrence Livermore Labs. And the reason they do this is not to generate power. This is not an effective method of generating power. It really is to study how fusion works so you can design nuclear weapons. That's why the money is there for it. But it's cool because they have these massive things that shoot lasers from all directions at this little falling pellet. It's crazy cool. And you do interesting science, but where the money comes from is so you can use the information you get out of this for understanding how you use it for nuclear weapons. Now, magnetic confinement is the way you actually do real fusion power, where a donut-shaped magnetic field will hold the plasma because it's charged. The charged particles get bent by magnetic fields. So if you make an appropriately shaped magnetic field, you can keep the charged particles contained, while electric currents will raise the temperature of the plasma. So magnetic and electric fields are useful since a plasma is a gas of charged particles, and thus you can manipulate them with electric and magnetic fields. And the leading labs for fusion research using magnetic confinement, well, they're MIT and Princeton, but really the big research stuff these days is all in Europe. They're building a test reactor right now in Europe. So, some advantages of fusion over fission. Deuterium is abundant and cheap. It can be extracted inexpensively from water. The nuclear waste disposal, relatively few radioactive byproducts, and they have relatively short half-lives. The nuclear waste disposal is relatively straightforward. Fusion reactors can't get out of control. In the event of a system failure, the whole thing just cools down quickly. They're not dependent on a critical mass. They're not self-sustaining. You're putting a lot of effort to get fusion to occur. So when something goes wrong, the fusion just stops. So nuclear reactions are tied to energy. In 1905, Einstein published his special theory of relativity, which deals with the changes that occur in mass, length, and time as an object's speed approaches the speed of light. And this theory predicts that the mass and energy are not separate entities. The mass and energy are related to each other. They're not actually separate entities, but mass is sort of like frozen in, is energy. Mass and energy are the same thing. And they're related by this famous equation, E equals mc squared. So if you see E equals mc squared, that's how you convert mass into energy, and vice versa. And Einstein's predictions have proved correct. So scientists have been able to change mass into energy, and on a very small scale, energy into mass. So 1 gram of mass has an energy of something like 90 trillion joules, which is the same amount of energy released by 20,000 tons of TNT. And what happens is that in a nuclear reaction, well, in like fission or fusion, both of those, the starting mass is slightly larger than the ending mass, and that is turned into energy. And that's why they can release so much energy. So calculations with Einstein's formula equals mc squared have convinced many scientists that the small amounts of mass that are lost in nuclear reactions could be a tremendous source of energy. We can actually measure it, and the amount of energy released matches the amount of mass that gets lost. And to determine the change of mass in a nuclear reaction, we can simply add up the masses of all the reactants and subtract the masses of the products. And generally, during a nuclear reaction, mass is either gained or lost. And in the fission of uranium, mass is lost, and in the fusion of hydrogen, mass is lost. And in both those cases, energy is gained. And that mass defect is measured in mega electron volts, usually, which is 1.6 times 10⁻13 joules as a unit. And if it's an endoergodic reaction, an increase of mass takes place during the reaction. So you absorb energy by the number of atomic mass units times 931 mega electron volts per mass unit. A decrease in mass occurs, you release energy by the number of atomic mass units times 931 mega electron volts per mass unit. So here, going from uranium-236 to krypton-88, barium-144, and 4 neutrons, we have 236.04556U. It goes to 87.91445U plus 143.92284U plus 4 times 1000867U. So the total mass on the left side is 236.0445556U. Total mass on the right is 235.87197U. So there's a difference of 0.17359U. So for every uranium-236 that splits, 162 mega electron volts of energy are released. Now the sun is converting millions of tons of mass into energy daily, every second. So for fusion, deuterium-tritium fusion, we have 2.0140U plus 3.0161U goes to 4.0026U plus 1.0087U. We go from 5.0301U to 5.0113U, and the difference is 0.0118U. So you get 17.5 mega electron volts per fusion event. On a kilogram for kilogram comparison, you get more energy from fusion than from fission. So the fission of 1 kilogram of uranium-235 produces energy equal to the burning of 2 million kilograms of coal, while the fusion of 1 kilogram of deuterium releases energy equal to the burning of 40 million kilograms of coal. It's about 20 times better on a kilogram per kilogram basis of fuel, but deuterium is a lot easier to get than uranium. And a lot easier to deal with than uranium. So here you can see the energy release in both nuclear fission and fusion. Any reaction that leads upward on this curve releases energy because such a reaction is accompanied by a mass defect. These are the relative stability. The peak of this is iron, 56. And that is why the cores of stars, when a star finally starts fusing up to iron, that is the point where a large heavy star will die, because the iron will not generate any energy in fusion. Your core will get full of iron, collapse, and the star will explode because of that. So fission proceeds from right to left, this way. Fusion proceeds from left to right, this way. And the top of the curve is iron 56. No net energy is released either by splitting or fusing iron-56. Now, radiation has effects on your biology. Mainly this is because the radiation released has some energy that can affect and damage molecules. Those molecules may be important to your biology, like your DNA. So ionizing radiation is radiation that is strong enough to knock electrons off of atoms and form ions. Ionizing radiation includes alpha particles, beta particles, gamma particles, neutrons, gamma rays, and X-ray. These types of radiation can also harm or kill living cells, and are especially harmful if they affect molecules involved in cell reproduction. So if you're exposed to a lot of radiation, it can tear up your DNA. And then your cells stop reproducing, and then they die, and that is bad. And it cannot be seen, smelled, felt, or tasted. None of those have anything you would notice. So the common way you measure them is with film badges that react to that radiation and change color. And the effects of radiation on living organisms can be classified into two categories. There's somatic effects, which are short and long-term effects on the recipient of the radiation. These are things like acute radiation sickness can give you burns and things like that. Can cause extreme local damage, but also it can give you cancer. And then genetic effects, which are defects in the recipient's subsequent offspring, because it can damage the DNA you pass on to your offspring. And radiation units, there is the REM, which is the Roentgen equivalent for man, which is the unit used to discuss biological effects of radiation. There's a million radiation units. They're all weirdly, subtly different and are confusing. This unit takes into consideration the relative ionizing power of each type of radiation and its effects on humans. The average US citizen receives 0.2 REMs per year from a number of different sources, both natural and man-made. A small amount of radiation exposure is just inevitable. It exists in the environment we live in, and a lot of it is just natural. But certain activities will cause you to have more radiation exposure, like taking a plane flight. Because you go higher up in the atmosphere, you're exposed to more radiation from space. So 0.2 REM is the average annual radiation exposure for a person in the US. So sources, biggest source is radon coming from the ground. It's bad if you have a radon leak. So the problem with radon is that it's a gas and it can accumulate and it's heavier than air. So if you have like a radon leak in your house, that's a problem. You need to do something about it because it will like concentrate in your basement. But the solution is you seal your basement so the radon doesn't come in. Because it will just dissipate into the atmosphere and not be a big deal. But radon is the biggest source, just in general. Then soil and rocks. There's some just internal generated radiation in your body, because some of the elements that make up your body have radioactive isotopes. Then cosmic rays, unless you fly a lot, then that's going to be higher, because you get more cosmic rays when you go higher up in the atmosphere in a plane. So your radiation exposure increases a small amount when you take a flight. It's not a big deal, but it is a fact. Then medical X-rays, nuclear medicine, consumer products, and other. But don't buy anything called negative ion, because most of those A, don't do anything, and B, a lot of them are dangerously radioactive. And so you should not buy Croc things that can make you sick. So there are natural sources like cosmic radiation and high altitude rock areas. There could be radiation in both bedrock, and then there are radionuclide that you ingest, like carbon-14 and potassium-40. So in fact, one of the measurements of radiation is the radiation of the standard banana of radiation. Bananas have a lot of potassium, so they're slightly more radioactive than almost every other thing. Not a big deal. and you need potassium to live. But yeah, like radon gas from bedrock varies greatly with location, but it can cause a lot of problems because it can give you lung cancer. Because you breathe it, the insides of your lungs get exposed to radioactivity. That's not good. And then there are anthropogenic sources, things like medical x-rays and treatments, TVs, tobacco smoke, nuclear waste, certain household products, coal power plants that comes out of, Now, the long-term cumulative effects of radiation are not understood. There's a lot of debate about whether a tiny amount of radiation is good for you or bad for you. Or neither. Yeah. But without a doubt, the most common long-term somatic effect is an increased likelihood of developing cancer. And lots of earlier workers with radionuclides died of cancer, and these scientists were generally exposed to small doses over many years. So, for example, you may have heard of Marie Curie. She was one of the discoverers of radiation, had 2 Nobel Prizes. She died of cancer because of the exposure she had to various radionuclides. Her husband did not die of cancer because he was hit by a streetcar. He probably would have had he not been hit by a streetcar, but he was hit by a streetcar. But yes, there does not appear to be any lower limit below which the effects are negligible. There is a point where you just shouldn't worry because it's not worth it. But avoiding radiation is generally any exposure to radiation should be taken seriously. The environmental stuff you can't deal with, just pay attention. So, but a lot of sources of radiation aren't as dangerous as you might think. Like alpha rays and beta rays aren't that dangerous because they're easy to block. Alpha and beta particles are electrically charged. They can be easily stopped. Basically, alpha particle exposure to an alpha source from the outside isn't a problem. Eating an alpha source is really bad. Basically, the dead layer of skin you have on the outside of your skin is enough to block alpha particles. You can block them with like a sheet of paper. And beta particles don't penetrate very far either. But if you consume an alpha source, that can be really bad because they're big, heavy particles, so they can do a lot of damage if they can actually get to stuff. Gamma rays, X-rays, and neutrons are more difficult to stop because they're not charged particles, so they don't interact as much. So they can penetrate quite a bit. And that's why your doctor wears, that's why the technician at the X-ray machine wears a lead apron. And by the 1930s, scientists had identified 4 subatomic particles: the electron, proton, neutron, and photon. More than 200 elementary particles have been identified, mostly from within the nucleus. So they're exchange particles responsible for the 4 fundamental interactions: electromagnetic, strong, weak, and maybe gravitational. Gravity is weird. But we've identified lots of elementary particles. But we can boil it down to what's called the Standard Model, which has about 16, 17 particles that everything is built up of. 6 quarks, 6 leptons. Oh, then there are antiquarks and antileptons. So that's another set. Yeah, there's a problem. Well, a bunch of them. But 200 or so elementary particles is a little high, but it's a few dozen. But the elementary particles include things like simple combinations of quarks, but we're not going into that. Because protons, and neutrons, for example, are made up of subparticles called quarks. And so there's a whole bunch of different particles you can make from various quarks. Let's see, exchange particles, there's 5, 5. And then maybe 6. 7, yeah. So particle accelerators are used to study elementary particles. The biggest one currently active, is the Large Hadron Collider near Geneva in Switzerland. It became operational in 2010 after nearly 20 years of building. It's the largest particle accelerator built so far. The second largest particle accelerator in the world is the Tevatron. It's in a couple hours west of here, maybe not even that. It's at Fermilab, which is in the western suburbs of Chicago. But it is smaller than the Large Hadron Collider. So there's an inconsistency in the standard model due to a large mass difference between certain exchange particles. This led to the proposal of the Higgs boson, which would explain why particles have mass. And in 2012, a new particle was discovered with the Large Hadron Collider that was consistent with the Higgs boson. Unfortunately, it was like the least interesting version of a particle that was consistent with the Higgs boson. And every particle has an antiparticle. An antiparticle is basically the same particle, but with the charge flipped and some other things flipped. It actually very much looks like that particle traveling backwards through time. And when a particle and an antiparticle meet, they annihilate each other and release energy. So the antiparticle for the electron is the positron. So we've seen these plus electrons. Those are positrons. They're anti-electrons. And that's the end of chapter 10. So the neutron number is the mass number minus the atomic number, and E equals mc squared is the mass energy relationship. So that is it. I will see you all next week on Monday, when we will have the review of chapters 5, 6, and 7, and the chapter 7 quiz. Then on Wednesday next week, we will have the test on chapters 5, 6, and 7. And the lab period on Monday next week is for makeups, but if you have anything else you need to make up, I'm also available earlier in the day on Mondays, Tuesdays, and Wednesdays. Any questions? Okay, have a nice day. We'll see you guys next week.